Okay, so it's a great pleasure for me to introduce our next speaker, Saikat Guha. I'm very happy he could make it. I think Saikat attended also the first EACN already, and at least to me and then to my group, this was quite inspiring. So Saikat has now moved to University of Maryland. He's a Clark Distinguished Professor. Before that was at University of Arizona, where also Bulat Bash is still. And who knows where you will be next? And then, he did his PhD with Jeffrey Shapiro. I think, from my perspective, at least a legend in optics, and started with multi-user information theory from this optics. But he then also went to industry. Yeah? He worked for Raytheon or for sub company in Raytheon. And now, with I think a lot of knowledge obtained in all those years about information theory and optical communication, he is going to enlighten us how to bring quantum communications in the optical domain from theory to practice, which I think is totally in line with the scope of this workshop. It's my great pleasure, Saikat.
Thank you, Yanis. Thanks for inviting me. Thank you very much, Yanis, and all the organizers, Christian, Bulat, everybody, Arun, for hosting. I asked Bulat what he wanted me to present on, and this is what Bulat wrote me in an email. So that's the topic of my talk today. I'll try to give you some perspectives on bridging between theory and where experiments currently stand in a variety of different places where quantum techniques are considered useful in different ways for optical communications. We had some wonderful talks this morning, so that makes my life a lot easier to position the messaging and my talk. So my plan is to spend roughly a third of my time or half of my time talking about role of quantum in classical communications. So this will touch on some of the things that we heard from Matthew, for example, in the morning. And then I will talk about quantum communications, where we will talk about transmitting qubits reliably over a quantum channel and associated problems. So let's start with classical communications. I just made this slide while I was listening to Matthew's talk, and I think some of the things are, this is just my thinking of how I classify different ways and regimes in which quantum can help communications. So the first bullet point there is about, so you have an optical communications channel, laser communications channel. You're sending classical data bits, and you are in a very low received photon flux regime. So this is where you will be, say, if you're doing deep space optical communications, for example, and low thermal background. High losses, so that's why you are receiving very little photons per pulse to your receiver. So in this regime, quantum receivers that act collectively on many modulated laser light symbols can give you higher capacity or much higher bits per photon or photon efficiency compared to absolutely any receiver that acts on one symbol at a time. Okay, so this is one place where quantum can help. Another place where quantum can help, and this is lesser well known, and I'll show you a couple of results from in this area. Traditional laser communications, so fiber communications, you have bright laser light pulses, again, low thermal background. Loss doesn't really matter because I'm talking about high received photon flux. There are receivers that are non-traditional receivers. If you have heard about Kennedy receiver or the Bondurant receiver, things like that, that use semi-classically describable optical operations, but doesn't quite detect the laser light modulated pulse using one of the conventional optical receivers. It doesn't benefit so much in terms of capacity, but you could benefit significantly in terms of what is known as the reliability function or the latency of communication. So that's a niche application. If you have, for example, bursty communications where you want to send a big chunk of data with a low error probability over a short period of time, these receivers could be useful. Okay, so we heard a lot from Matthew about the third bullet point, low transmitter brightness, high thermal noise regime. and high loss. We know that pre-shared entanglement between the sender and the receiver could go way further in terms of communications capacity, even over and beyond what the Holevo limit gives you, which doesn't use pre-shared entanglement. And then I'll touch on one recent paper, and this is a whole area of the fourth bullet point. Traditional laser communications, again, high transmitted receive photon flux, but in a low loss regime, unlike the second bullet point, which is high loss. So in that regime, where a quantum signature that is riding on top of your strong optical laser pulses do have a chance to survive the channel, you can augment traditional classical laser communications with quantum properties for example, improved resilience and so forth. Okay, so I'll give you 1 to 2 slides on each of these 4 just to show you the kinds of things that show up in these areas of applications of quantum. Okay, so let's start with this simple example. So I have a binary phase shifting modulation. So you have, and let's take alpha to be a real number. So if I hand you one of these 8 code words, each one is 5 time slots, and you have of the 32 possible code words, you only have 8 in your code book. And I tell you, design the receiver that minimizes the probability of error of choosing between them. The first step is, how do you calculate the probability of error? Well, what you do is that you calculate the UN Kennedy and lax conditions of discriminating between these 8 pure states whose inner products are given by the inner product between alpha and minus alpha raised to the Hamming distance between the ith and the jth code word. So that's easy. You can calculate that number and you can plot it as a function of the mean photon number per mode, and you get something like this. The pink line is the block error probability as a function of the mean energy per pulse. And then you think about, well, how would you design a receiver in the lab right now if you were to tell apart between alpha and minus alpha? You would probably build homodie receiver. You would beat every received pulse with a strong local oscillator, and then you difference amplify the photocurrents of the 2 outputs, and you integrate over the pulse duration. No matter what receiver you use that detects each of those 5 time bins one at a time, followed by any classical post-processing, including soft information processing, you cannot go beyond that blue dotted line. So in order to bridge the performance between the blue dotted line to the pink line, you have to use some form of joint detection, some form of a quantum detection. So this is a classic case of what Charlie Bennett called originally non-locality without entanglement. You're starting with a product state, but you use entanglement in your receiver, entangling measurements to get better performance than you cannot otherwise. I will not go into the details here, but I'm going to point out to two important results here. So that 2013 paper I did with my colleague Marcus Silva and Zach Dutton, there we said, well, if I give you one of 2 coherent states, alpha and minus alpha, with a real valued inner product, you know that that's worth 1 qubit of information. Why? Because if there is a scalar inner product between 2 states, if I hand you one of those 2 with a promise that I'm only giving you one of those 2, you should be able to prepare 2 states of a single qubit with that scalar inner product. And there ought to be a map between those 2 states to the 2 states of the qubit. I'm saying ought to, it's not easy at all. But if you can figure out that mapping, then your optimum receiver is just a 5 qubit quantum computer. Well, then the next question is that, do you really need 5 qubits to store the information? There are 8 possible code words I'm giving you. So that if you also have the information about the code book, then you should have only need 3 qubits to compressively load the information in that 5 pulses. So it's a small, tiny 3 qubit quantum processor, which could give you this communication super additivity that Matthew was talking about in the morning. So with that in mind, in 2022, I collaborated with my former postdoc, Kaushik Sheshadri-san, and Narayanan Rangaswamy. He's both of them now are faculty. Narayanan is at Arizona and Kaushik at Pittsburgh, along with Henry Pfister, to work off of some ideas that Joe Rennes had first published on quantum version of belief propagation, that acts on the factor graph of a code that can achieve the performance given by those black crosses. So it meets the Hellstrom bound, and we can prove that you can meet the Hellstrom bound for any code whose factor graph is a tree. Joe has another paper, 2022, that goes beyond our original result. And there was a small experiment that was demonstrated on a Honeywell strapped ion quantum computer on a 3-qubit version of this result, which was this 2022 paper with Prinaha Narang and others. And you could also look at this last paper with Don Borison and Johannes Beauregard and Kelly Smith. And there we actually have a recipe on how you could use light matter interactions that are commonly known for encoding dual rail qubits, single photon in 2 modes, into atomic memories using what is known as the Duan-Gimbel interaction. I'll talk a little bit more about that in my quantum communication part of my talk, in order for you to achieve the quantum limited state discrimination. Okay, so this is a broad area. There's lots and lots of open questions here in designing receivers that utilize either optical domain in quantum operations and in atomic qubit domain quantum operations. So there was a paper I wrote in 2011 where I proposed something that was I call the green machine, which is actually a word I borrowed from the classical error correction literature. I learned about that from a course I took as a grad student from Dave Forney's class at MIT. It's a circuit made up of these butterfly elements that add and subtract 2 numbers to decode Reed-Muller codes. So it turns out that if you make this circuit of beam splitters, passive linear optical circuit, it can transform a binary phase modulated Hadamard code word into a pulse position modulation code word. Meaning if you enter one of those vertical columns of plus and minus, plus minus denotes alpha minus alpha, on the output, all of the energy gets concentrated onto one of the modes. And then if you do photon detection on the output, it induces an memory erasure channel. And if you calculate the Shannon capacity of that, and divide by the number of modes, so this vertical column is in time, so you have the alpha minus alpha in time, the number of bits you can transmit per mode is higher than any receiver that acts on one mode at a time, one optical pulse at a time. So this is called super additivity, meaning a receiver that can achieve capacity that's higher than symbol by symbol measurements. And recently we did a experimental demonstration of that in my lab led by Chauhan Sui. He was a student at University of Arizona, but he's now a research faculty at University of Maryland. My student, Jack Postlethwaite, he's a current PhD student. And the main trick here was to realize that in the green machine, you see these 3 columns of beam splitters. There's a very interesting way to time delay these 8 pulses in time so that one beam splitter actually implements each column, but in time. So for an N-mode green machine, you only need log N stages. So that made the experiment so much easier. And this archive paper, which is in review right now, generalizes the concept for arbitrary temporal mode transformations, which has applications in classical communications, but also other applications in sensing. This is what it looks like in the lab. It's a fiber-based setup, which we moved from Tucson to Maryland. And it was lost by FedEx, and we were paranoid for a month and then finally located in a warehouse in the Phoenix airport. But it was a couple of modulators broken, but Jack is fixing that and building that ahead for the new design. Haiwan Chang, she was a PhD student at MIT in 2011 with Li Zhong Zheng, and she worked with me and Li Zhong. And her PhD thesis, she explored design of optical receivers, joint detection receivers, that only use things that can be described using the semi-classical theory of photodetection. So what I mean by that, coherent states, mixing on linear optical elements, local oscillator lasers, and photon detectors, whose output can be described by Poisson shot noise. So nothing beyond that. So no squeezing, for example. And her thesis resulted in this paper, which was a big no-go result, unfortunately. But the result can be summarized as follows. So the y-axis here is the bits per photon. So number of bits you're encoding per photon. So if you have a BPSK coherent state code word, say you're modulating with alpha and minus alpha. So each mode, each pulse is carrying alpha square photons. And if you number of bits you encode per pulse, if that is C of n, where n is magnitude alpha squared, C of n is bits per pulse and n is photons per pulse. I'm dividing C of n by n, so I get bits per photon. So that's the y-axis. And I'm plotting that as a function of the mean energy per pulse n. The Holevo capacity, the fundamental limit of capacity, that's that G function you saw in Matthew's talk. If you were to plot that in the mean photon number, small mean photon number regime, if you do it, oh, there's a typo here. This should be plus n, not plus 1. So C infinity, the Holevo capacity goes as minus n log n plus n. Whereas what Haiwan proved is that my green machine receiver design, not just that, but any receiver whose workings can be described by semi-classical theory of optics, the second term in the Taylor series expansion was minus n log 1 over n. So you cannot beat that, unfortunately. So you have to use things like squeezing and so forth. And if you look at Haiwan's paper, she looks at a very general receiver that is semi-classically describable. So what she does is that she takes these n coherent states. So this is your received code word. X1, X2, these can be any coherent state, amplitude or phase modulated. She also brings in a bunch of vacuum modes and puts it into this massive passive linear optical unitary. And then she peels out a tiny bit of only the first mode, which has a tiny bit of photons, the coherent state. So this is a tensor product coherent states to the output. And she applies a displacement, phase space displacement, followed by photon detection. Okay, and then she takes that photon detection on-off output and then uses that to determine another big passive linear optical unitary on the rest of the coherent states and keeps going. So this subsumes the Dolinar receiver, the Kennedy receiver, the green machine, or everything known and also possibly future things that you could do. And that doesn't work, basically. So lots of open questions. Well, first, we know that you have to use non-Gaussian resources, but how do you use that in a structured way that utilizes the properties and underlying structure of codes? For example, Mark Bildy and I did this paper on CQ polar codes back in 2012. Can we utilize the structure of the polarization for CQ polar codes to come up with receiver designs that obviously they will use non-Gaussian elements, but perhaps they are simpler and easy to think about. Another paper I want to point you out, this is in review right now. Non-Gaussian interactions are hard to realize in optics. One of the most prominent non-Gaussian interactions in propagation is the Kerr interaction. The Kerr interaction is a phase modulation where the phase is proportional to the intensity. So you can have a self-Kerr or a cross-Kerr. If you have cross-Kerr, means if I have n photons here, you apply a phase on the other mode, which is proportional to n. If you had a cross-Kerr interaction that can apply a pi phase shift for a single photon, then you could do a controlled phase gate on dual rail qubits. This was in fact part of the original KLM proposal in 2001, but turns out that it's exceedingly hard to do a pi phase cross-Kerr. In fact, there are several leading groups. For example, Alex Gaeta, who is now in Columbia University, his group pioneers on-chip realization of cross-Kerr interactions in photonic waveguides and cavities. And he has gotten to something like 10 to the minus 3 radians per mode of cross-Kerr. But there is a beautiful effect that I borrowed from some work I learned from my colleague Christian Ahrens's work. He calls it Hamiltonian amplification, which is a weird terminology, but once I understood what he was doing, I found it was very, very interesting. So the idea in the context of what we are doing here is that U delta T is a delta T propagation, delta T time application of a tiny cross-Kerr interaction. And if you were to get to a pi phase cross-Kerr, let's say you have a pi by 1,000 cross-Kerr, you could apply 1,000 times. But the problem is that if each one has a loss that is quantified by a beam splitter interaction of transmissivity eta, you will have an eta raised to 1,000 overall transmissivity, which will make it completely useless. But if you were to sandwich each of those cross-Kerr interactions with a squeezer and an anti-squeezer on the two sides in a clever way, then you may need only 6 of those to get to pi phase cross-Kerr. So you get eta to the 6 instead of eta to the 1,000 of loss accumulation. It's a beautiful idea, and I believe this works for other non-Gaussian operations too, not just cross-Kerr. It's a very general concept. So the Gaussian operation that comes from squeezing that pours itself into the non-Gaussianity without the losses accumulating. So that might be another trick of the trade that we could use to construct receivers. Okay, so let me talk about the second bullet point. Any questions, comments about this first area of receiver designs for communications? Feel free to interrupt me if you want, because I have a few topics that I'm going to cover today. I don't.
Go back
Mhm.
The semi-classical. I once limited semi-classical, but then you were talking about Gaussian limit. Is there a Gaussian curve somewhere there as well?
Yeah, good question, Bulat. So if you have passive linear optics and photon detection, that is semi-classical, but it's non-Gaussian because photon detection is non-Gaussian. So what Bulat's question is, if you have only Gaussian operations, meaning Gaussian unitaries and Gaussian measurements to design a joint detection receiver, Masahiro Takioka and I have a paper in 2015 where we proved, it was a long proof for a no-go result that said that you can work a lot, very hard if you want to build joint detection receiver. The maximum Shannon capacity you can get can be achieved by just time multiplexing between a single mode homodyne and single mode heterodyne detection. So it's a PRA. I can send you the link. So it's interesting because you need, if you just have photon detection linear optics, if you throw in Gaussian into, if you just throw in squeezing into this mix, there is a very famous result by Seth Lloyd and Sam Brownstein that shows that this is universal. Meaning, if you have only beam splitters and squeezers and photon detectors, that's universal. So you should be able to do whatever you want, any unitary, any measurement, any quantum state preparation. But that's easier said than done. There's a very nice paper by Peter Van Loek, and Sefi is the last name of the first author, where they showed that a repeated application of these BCH commutators, you can approach any non-Gaussian unitary as closely as you wish in trace distance. But that construction is iterative and it's not that useful. So the better way to think about would be to use the structure of the problem and the codes, for example, to come up with receiver design. So it's this whole area of bosonic circuit synthesis is quite an interesting area. Okay, so let's talk a little bit about the second topic. And I just have a single slide on this because I wanted to motivate. This is not that well-known an area. You might have heard about the Kennedy receiver. The Kennedy receiver tells apart between two coherent states, alpha and minus alpha, by first displacing the constellation to 0 and 2 alpha, and then doing photon detection. So you apply displacement and do photon detection. A generalization of that Kennedy receiver for arbitrary constellations was proposed by me, Sihui Tan, and Ranjit Nair in the 2014 paper. And we proved a result where we said that, say, for example, if I give you a phase shifting modulation that you were seeing in Matthew's talk, so but applied on coherent state, and the use heterodyne detection receiver, for example, you'd get a probability of error as a function of mean photon number. And there is if you calculate the Hellstrom limit, the minimum probability of error, you get another probability of error curve, which is this dotted line. And there's a factor of 4 gap in the error probability exponent. Turns out that the sequential nulling receiver can achieve this optimum Hellstrom error probability exponent. That this factor of 4 between this sequential waveform nulling receiver and heterodyne detection, it's very general. You could pick QAM constellation, or absolutely any phase amplitude constellation. This works. But this is an error probability at the symbol level. What does that mean for capacity? Well, turns out that the capacity-wise, the performance improvement is not as pronounced compared to heterodyne. So let me walk you through this plot here. So I'm plotting capacity in bits per pulse or bits per mode as a function of mean photon number per mode. The black dashed line is Holevo capacity. Look at the blue lines and the red lines. Okay, so the red lines correspond to heterodyne detection for phase shifting modulation. BPSK, QPSK, 8PSK, and 16PSK. So obviously when N becomes high, the capacity goes to log M number of bits, obviously, right? Because at that point you can tell apart between the 4 states of the constellation precisely. So the red and the blue both go to log M, but the blue gets there quicker. Like convergence is quicker. That's the sequential waveform nulling receiver. But the overall envelope of the blue and the overall envelope of the red, there's a tiny bit of a gap, not that much. But then when you look at the reliability function, so what I'm plotting, what I'm writing here, this is Bob Gallagher had defined it in the context of classical data communication. Your block error probability can be written as e to the minus n times this reliability function, which is a function of the rate, as long as your rate is less than capacity. So if you plot the reliability function is very hard to compute, by the way, but you can calculate. Bob Gallagher's book showed how you can calculate a lower bound and an upper bound to the reliability function. So Sihui Tan in this 2015 paper, she calculated the upper and the lower bound from Gallagher's for the reliability function for the SWN, the sequential nulling receiver, and heterodyne, this for 4 PSK. And she found that now you can get say a factor of 3 to 4 improvement. And what this is going to translate to is an improved latency of communications, meaning you'll get the same probability of error, but maybe with a 4 times shorter code word if you were to use these receivers. So this is another important, interesting application of a quantum-inspired receiver, but in a totally different regime of high photon number. Okay, so entanglement-assisted communication. So this is a topic we heard a lot from Matthew this morning. So I'll just show you one slide on this and a couple of points I'll make about this. So this is the setup that we considered in this paper that Bulat and I wrote with Juntao Zhuang in 2020 ISIT. That's the first reference there. So ideal two-mode squeeze vacuum states pre-shared by Alice and Bob, and Alice does a phase modulation on her end. And Bob does a joint detection receiver. We had a couple of prescriptions of joint detection receiver that my student Ali Cox, he improved upon in that second reference, which essentially showed that you get that CE over C, the entanglement assisted capacity as a divided by the Holevo capacity to scale as log of 1 over NS. But there is still a constant factor gap between that actual CE. In this 2023 paper, Ali shows that there is a certain pre-processing you can do to the receive side if you were to use TMSV and phase modulation that translates the problem into discriminating between coherent states. So any innovation you make on receiver designs, the first part of my talk that I gave carries over to this problem of entanglement-assisted communications. But I want to make a couple of observations here. So this problem is very closely related to the problem of quantum illumination receivers. So there are ideas that can be borrowed from the quantum illumination problem, which go into the receiver design for entanglement-assisted communications. And another thing, I think this is a question that was brought up by Christian in the morning about what about imperfect entanglement? Right? So that's, and Matthew and I had quite a bit of discussion about that and discrete variable entanglement. Because as I will talk about in my quantum communication portion of my talk, is that everything, like everybody is working on entangling qubits. Entanglement distillation protocols, entanglement heralded entanglement generation protocol. You are generating qubit entanglement between spin-based memories or superconducting memories or trap-time memories. Can you leverage DV entanglement, but with certain light matter interactions like the Duan-Kimball scheme that are available to us that people have demonstrated to achieve that same CE? Like, is there a way to use this digitized quantum information to achieve this entanglement set capacity? And that's an open area that will be very, very interesting. Not just that, can you take imperfect entanglement, meaning lossy TMSV, for example, and utilize that to do entanglement-assisted communications, but first apply entanglement purification or distillation in the optical domain, which will necessarily require non-Gaussian operations like photon subtraction, photon catalysis, non-deterministic linear amplification, and so forth. Okay, so let me talk about a little bit about this this one more result on the classical communication side, and then I'll speak about quantum communications. So here we will consider another regime of this is a traditional optical communications, laser communications, but in a low loss regime. So you have binary phase modulated pulses. So each of those coherent states, after you generate them, you apply a plus or minus phase. And say they are going over a lossy bosonic channel, eta 1 is the transmissivity, and say eta 1 is high. So you have a low loss channel, say 0.9, for example. So it's a local area communication channel. And say you're using a homodyne detection for the receiver side. So every homodyne detection output is a Gaussian distributed random variable with a mean of square root of eta 1 alpha and variance of 1/4. Now, at an unknown time, somebody comes in and introduces a tap in your fiber. Okay, so your transmissivity, your loss, now goes from eta 1 to eta 1 times eta tap. So your transmissivity drops from eta 1 to eta 2. So eta 2 is eta 1 times eta tap. And your job is to catch them in the act as quickly as possible. You want to declare that there was a tap introduced in the fiber. What is the quickest that you can detect that tap? So there's a very, very old theory developed by a guy called Page from 1954. And that area is known as change detection. So the classical version of the problem is that I'm handing you copies of a random variable from a distribution P. And suddenly, without telling you, I start handing you samples from a random distribution, random variable Q. And you know P and Q, but you have to catch me in that. So the latency with which you can catch me given a desired level of confidence is proportional to the inverse of the relative entropy of Q to P. And the quantum case, that is replaced by the quantum relative entropy between the post and the pre-change. So that paper came out 2 years back. Konrad Ordenard, the same person who invented the quantum Chernoff exponent, he's the first author on that paper. So anyway, so we consider a couple of very simple things in this situation for bosonic communication. So we said, well, instead of coherent state, binary phase modulation, what if I put a little bit of squeezing on every pulse? So alpha R is a displaced squeeze state. So alpha square is the mean photon number n, and let's say n is a large number, say n is 100 photons per pulse. And n sub a, which is the amount of photons attributable to squeezing, let's say it's 0.1, like 1,000-fold less compared to the coherence energy. So that I'm calling NA, A stands for augmentation. So N is the mean photon number for classical, NA is the quantum photons. And to be fair to the classical one, I'm just giving NA plus N number of photons to the coherent state. Now the Gaussian distribution looks a little bit more complicated. The variance changes to because of squeezing. And then I consider a slightly even more advanced version of the quantum augmentation. Here, I take a squeeze-like pulse, so 0s is a squeezed vacuum, and say sine hyperbolic square s, which is the mean photon number in that squeezed vacuum, that says 4 times Na. And I split that in a green machine. So what I get on the top of that yellow box is a 4-mode entangled state where each mode has Na photons, because I've split the squeeze vacuum into 4 modes. Now I apply displacements d alpha or d minus alpha. That's the classical modulation part. So now my code words, the classical part of the modulation is governed by a classical error correction code. So now you have classical BPSK modulation, but you're basically spray painting this very weak quantum entangled signature on blocks of 4 pulses at a time. So that number 4, I'm calling little n. So n is something that you can go from 4, 8, 16, whatever you want. Okay, so these are the 3. This is the squeeze vac, the case B is basically the n equals to 1 version of the case C. It's a special case. So you can read the theory in my paper, which is in review, the first paper there. But basically it turns out that as you go from n equals to 1, 2, 3, 4, your latency drops very sharply. In fact, the derivative of the relative entropy of the post to pre-changes distribution with respect to NA at NA equals to 0 is infinity, even for the case B. So there is a very sharp increase. And so this is a work being done in a DARPA-funded program called Quantum Augmented Networks, where we are trying to implement this in my lab in an experiment. Okay, so I'm going to move over now to the quantum communications, which is the second half of my talk. Sure. Yes.
One then,
Yes.
It's actually the very normal way the value. So there are different ways. I mean, with the type, and there's this method essentially Chernoff bound. So he has a clear way to work with that and. Any thoughts on whether that is so? And I also believe that the converse you looking at it clear back, right? Yes,
Right.
Lower bound is through the expurgation.
Exactly. Expurgation gives you a lower bound. So by the way, we did in that paper, we did not use the most advanced lower and upper bounds. We just used Gallagher's because we were basically trying to show, as you can see that it's not tight, right? Because there's a gap between so the lower and the upper bounds are quite far away. But it shows a clean separation between the sequential nulling and heterodyne receiver. So that's what we were trying to do, but it'll be interesting to use more advanced techniques to more precisely quantify the reliability function. And this is an interesting application of quantum or non-traditional receivers, which often gets overlooked. And this has quite a, it's much more realizable in near term than these joint detection receivers. And it has applications to low latency communications. So yeah, there are better techniques to calculate the reliability function that will be very interesting. Okay, let's talk about quantum communications. I'm going to start with what is quantum communication. So use the act of sending qubits from point A to point B reliably. So classical communications, well, we are all familiar with what we do is that you take packets of k data bits and you put them into an error correcting code, take n bits and you send it over some modulated, send it over some noisy channel, demodulate, decode, and you have the output back. You could do the exact same thing for quantum communication. Take a packets of k qubits and put it into an encoder. What's an encoder? It's a quantum computer. You bring in n minus k ancilla qubits, and you have an n qubit unitary operation. That's your encoder. So you generate an n qubit code word, which is an entangled state in general. You modulate them. Well, so for classical data communications, we have all these modulation formats like BPSK, QPSK, QAM, PPM, on-off keying, pulse amplitude modulation. For modulating qubits into photons, there are also different modulation formats. There's single rail, dual rail, GKP, CAT basis, bin basis, all sorts of modulation formats. So you pick your favorite modulation format, you send it over the noisy channel, and then you have a decoder, but the decoder cannot detect. It's a decoder that takes your code word and it puts into another quantum computer processor that produces fewer, the k data qubits that you send, hopefully with a fidelity high compared to your initial k qubit data packet. So this philosophy of communicating qubits over a noisy channel is known as one-way quantum communication. This is what we are familiar with in classical communications. But in quantum communications, there is another philosophy to do quantum communication. People call it two-way. So what's two-way? Two-way, what you do is that you first create an n pairs of qubits that are entangled, but in a noisy entangled state. You might do that by just sending n qubits over a noisy channel and then catching them on the other side, and you have n noisy entangled states. And then you apply decoding on both sides, and this decoder is known in the literature as entanglement distillation. And you distill k pure, high-quality entangled states, belt states across Alice and Bob. And then Alice takes her k qubit data packet, and then qubit by qubit, she teleports them using the k purified qubits that she got. Now, if you think about it, it's the same resource. You're still sending k data qubits. You're still using n uses of the noisy channel. But the underlying use of the channel, the resources and everything, that would be very different in terms of whether you use one-way or two-way. So two-way, people like to use two-ways because two-way, you start with a generic resource, this entangled states, which has other uses other than teleportation for qubits as well. Okay, so any question about this slide, Matthew? Yeah? Mhm. Very good point. Very good point. Yes. On the other hand, so what Matthew is referring to for teleportation, you have to still send that classical data. Now, that channel, if that channel is a bosonic channel, whose transmissivity eta is less than 1/2, then its one-way quantum capacity is 0. Because the capacity is log of eta over 1 minus eta. When eta is less than 1/2, it's 0. But the two-way capacity is minus log 1 minus eta, which is non-zero for any value of eta. So even for one-way communication, you would require that reconciliatory information. But you're absolutely right that the classical overhead in two-way generally is higher. So classical communications overhead is another very important part that often gets overlooked in designing quantum communication systems. But that's a good point, Matthew. Okay, so I'm going to stick with two-way for today's talk because that's where a lot of the experimental work and theory work is happening. Now, so no matter which way you do it, two-way or one-way, there is a capacity. So this is the formula I was just telling Matthew. So this log of 1 over 1 minus eta, that's the black line. If you plot that as a function of channel loss in dB, you see this portion that looks like a straight line in the log-log scale. So why? Because when eta is very small, that formula is roughly equals to 1.44 eta. And eta, if it's your loss in optical fiber, it goes as e to the minus alpha L, where L is the length of optical fiber. So which means that quantum communication rate scales exponentially with the distance. But when eta is high, that portion of the curve that shoots up to infinity in that high eta regime, we should not ignore that. Because there are many applications of quantum communication, for example, within a data center, within a campus network, within a small area network, where eta can be high. And we should think about communication scheme, modulation formats, distillation codes, and all sorts of protocol components that cater to that portion, that low loss portion, which I haven't seen much work yet in the literature. Okay, so when you hear the word quantum communications, people are usually referring to one of those three tasks. Sending qubits, generating entanglement, or generating shared secret keys. Doesn't matter which task you're talking about, the unit changes from qubits per second to e-bits per second to private bits per second, but the capacity is still the same, log 1 over 1 minus eta. Yes, and that's why that 2 in the numerator is very important. Thank you, Bulan. So that little 2 in the parenthesis that I put there, that denotes two-way classical communications, unlimited, as an additional resource. Very good point. Yep. Okay, so but if you want to beat this, you need to introduce something along the length of the optical fiber, which we call quantum repeaters. I'll see if I can get to repeaters today, depending on how long it takes me, but we'll mostly focus on that single link for the most of my next 5-10 minutes or so. So even within two-way, there are two different philosophies of generating entanglement. In the community, people call it either midpoint swap or midpoint source. So what's midpoint swap? You have two memories on two sides that emit photonic states that are entangled with the memory, and the photons fly to the middle of the channel. They meet on a beam splitter or some sort of a swapping device. And then that produces some outcomes that you're happy with, and you declare that the two memories are entangled. Midpoint source is that you have a photon-photon entangled source, like an SPDC source or a spontaneous four-wave mixing source or some sort of an atomic emitter-based source that emits photons that are entangled. The photons fly out to the two endpoints, and they get heralded, loaded onto the quantum memories. And the memories declare, oh, I heralded a photon. They communicate to the other guy, and then you have a shared entanglement. Okay, both of them have to share classical information. Yes? Go ahead.
I have one question.
Sure.
How important is timing on synchronization in such a scheme?
Good question. So that entanglement swap circuit I've written there, that's an excellent question Giannis asked. What about timing? When do those photonic qubits arrive there? So there are two ways to think about that swap. One is a photonic swap, like a beam splitter. There the photons absolutely have to arrive at the same time. Or at least you need to know which photons that you're interfering correspond to which memory qubits in your register when you later reconcile your entanglement. But the rate of such protocols will necessarily be eta times eta will be eta squared. If the eta is the transmissivity on those two sides, you have to have both photons make it. There's a very nice paper from Misha Lukin's group in 2020. The first author is Mihir Bhaskar. The paper's title was Asynchronous Swaps Using Quantum Memories, where they take a photon from one side and load it into a silicon vacancy color center, and then load another photon that arrives at another time and loads that into that same spin, and then they make a single spin measurement that does a bell swap. And the rate of that scales as eta rather than eta squared. So there is some advantage to that blue box is generic. So you can have a synchronous swap or an asynchronous swap. Asynchronous swaps are in general better than synchronous swaps. That's a very good point. All right, so within these two, I'm going to now focus just on midpoint swap. So from one way, I went to one way, two way. Within two way, I'll just focus on midpoint swap. So midpoint swap, let's talk about the way we are generating these entangled states in the Center for Quantum Networks, which is a big center involving 10 universities, lots of PIs across the US. So this is a diagram from one of my colleague Dirk England's research group's papers. So this is a very simplified level diagram of the silicon vacancy color center qubit. What a silicon vacancy, if you have not heard about it, it's a silicon defect, that a silicon atom that replaces two nearby missing carbon atoms in a diamond lattice. And the free electron of that silicon atom, that serves as your qubit. And the way it serves as a qubit is that there's an external magnetic field that splits the ground state into two parts with using the Zeeman effect. That's the up and the down I'm showing in the bottom, separated by a microwave transition, which you can control. So you can do arbitrary single qubit gates. Those are your qubit levels. Now, the down prime and up prime are the Zeeman split levels of your first excited state of that same electron. And there's that red line, it's an optical transition between the down and the down prime, which is roughly 737 nanometers for silicon vacancy color centers. But the up and the up prime transition, it's slightly detuned away from 737. So meaning if I were to initialize my qubit in the up plus down state, and then excite it with a 737 nanometer bright laser, the down is going to go to down prime, but the up is going to stay where it is. Up is not going to go to up prime. And then down prime will emit a photon spontaneously and come back to down prime. So what ends up happening is that you get down, emits a photon, and up stays there. So you get an entangled state between the spin and a single rail photonic qubit that encodes a qubit in the presence or absence of a photon in the temporal mode. Now, I didn't have to stop there. Well, after I do this, so now I have these two cats denoting two time bins. What I could do is that I could apply a pi pulse, which is a flip to the spin, because I told you I could do any single qubit gate on the spin qubit. So I could flip the up and the down. And what happens now if I apply again another laser pulse, 737 nanometer? Now the down will emit a photon, but this time the photon will appear in the second time bin. So I have a state that looks like up 1, 0 plus down 0, 1. So this is again a Bell state, but between the spin qubit and a dual rail photonic qubit. Okay, so you can do both. So the first question arises that which one does better? So that was something that my former student Prajit Dhara worked out. So let's say this is just a cartoon of the color center. So that the red circle is the electron spin that talks to the optical photon, whose level diagram I was showing. And the blue circle is the nuclear spin, for example, in this case, the silicon-29 nuclear spin, which has a very strong coupling to the electron spin of that same atom, meaning Misha Lukin's group at Harvard University, they have demonstrated 95 to 97% fidelity, 2 qubit gates between the electron and the nuclear spin of the same color center. But what is very hard is to do 2 qubit gates between the 2 electron spins of 2 separate color centers. But you can do any 2 qubit gates between the nuclear electron spin of the same color center. You can do arbitrary single qubit gates on the electron spin and any single qubit measurement. Okay, so you emit a photonic qubit entangled with electron spin. It could be single or dual rail. You could do it from 2 sides and from 2 color centers and have that photon meet on a beam splitter after some frequency shifting to make sure that they are at the exact same frequency. And then you look for a success pattern. If it's single rail, you look for a click or a no click. If it's dual rail, you look for one of these 4 patterns of clicks and no clicks to declare a success. And then once you have a successful entangled state, you get an entangled state rho AB between the 2 electron spins. So this is the basic idea behind many, many experiments across the world on entangling color centers, neutral atoms, trapped ions, lots of different types of qubits. This is a basic problem. Yeah, question, Yanis, go ahead.
Yeah, the frequency shifting which you mentioned passing by, is that not also causing tons of problems, possibly?
Very good question. That itself involves that blue box that I just swept under the rug. That's the subject of research of 3 of the PIs in our center. That's a huge, huge topic. We could talk in more detail. There are certain, so there's one thing that Professor Marco Lonkar and my colleague Matt Eichenfield, they're looking at strain tuning. So the zero phonon line, the 737 nanometer on an unstrained diamond, if it's just one color center, it's a pristine color center there, it's changes by the local strain field on the diamond. So the question is that, there is a natural degeneracy of the color center, say in a 2D sample, but can you strain engineer the diamond to tune the color center ZPLs, the zero phonon lines, to match? Maybe instead of having all of them come to 737, maybe you have blocks of them that are at 737, another blocks at 736.8, and so on. So you actually make that bug into a feature, because then you can spectrally multiplex and use that to your advantage. Dirk Englund's group is also looking at serodyne frequency shifting, which is post-emission tuning, which is good and bad because it is more lossy because it's after the emission, but it's more controllable. So you can do post-emission tuning as well. And then there are also ways in which you can engineer them, these zero phonon lines, by embedding these color centers into nanopillars in diamond, which can also apply control strain to individual color centers in the sample. So that's an important thing, that you have to have that frequencies be exactly aligned. In fact, I'll come to this in my next slide, is where that rho AB that I'm talking about, that entangled state, if you were to write the density operator and calculate its hashing bound and distillable entanglement, what are the most important things, non-idealities? One is the quality of that overlap on that beam splitter, the mode overlap, which could result from spatial mode mismatch, spectral mode mismatch, and temporal mode mismatch. So if I take all of those things and write the overlap integral, call that quantity V, visibility of the interference. That V ideally should be 1, but maybe it's 0.99 or 0.98. That's one number. And the second thing that we care about is PD. PD is the excess noise or dark click probability of those detectors. And the third thing that we care about is the phase synchronization error, that epsilon parameter, which is the amount of carrier phase synchronization error, which only affects the single rail, the single photon scheme. The dual rail scheme, the only thing that matters is a mode overlap, the V parameter. So this is Prajit did a very detailed calculation of these schemes. And the crux of the story was that if you use the single rail scheme, it scales better. It scales as order square root of eta, which is square root of eta is the half channel loss. So that scales as capacity. But the dual rail one has a worse scaling. It goes as order eta. But the dual rail one is much more resilient to both V and PD. So if you look at the red family, so red goes to yellow when you turn on V, the visibility. And then when you turn on the dark click probability, in this case, I think he's taking 10 to the minus 6, or the numbers are over here, there's a crash, maximum range after which your distillable entanglement rate goes to 0. The y-axis here is the hashing quantity times the probability of success, whereas a single rail, it crashes much more rapidly. If you plot, you can look at the fidelity of the entangled state also instead of the hashing rate. But basic message here is that the dual rail is more stable. But very importantly, neither one of these schemes are capable of hitting that high capacity, high loss or low loss portion of the curve. Why? Because you're encoding 1 qubit per pulse. There's no way you can leverage that minus log 1 minus eta. You're limited to 1 EBIT at max per attempt. So there is no way you can get to that part of the curve. But this is what everybody uses because you are in the high loss regime, and it doesn't matter as much. Any more questions about this? Yes. Yeah, of course.
Sorry. I wanted to continue a little bit what Janis said, because I come from a different community with dealing with semiconductor systems. And for a long time, we had exactly the same problems, right? So frequency matching two emitters is very difficult. And the problem mostly comes from the fact that you can tune them, but you probably destroy your system somehow.
Yeah.
And what I found in the last couple of years is that I give up on this kind of approach of manipulating the emitters, but we can do this optically, completely optically.
Okay.
And using quantum frequency conversion. And yeah, one of the things is what you want to anyways convert it to telecom wavelengths, right? In these centers, for example, you need to do long distance things. You want to convert it to telecom frequency. And the frequency conversion can be tuned for each color center differently, or quantum emitter differently. And in that way, you can achieve that frequency overlap, right?
Exactly, absolutely. And that's exactly what we are doing right now also. So basically what you have is a Piplin nonlinear frequency converter with a tunable pump. That's what you end up doing at the end of the day. You're absolutely right. You pay the price of the inefficiency of the conversion, but at least it is heralded. So, and if it's all telecom, it's compatible with different kinds of emitters. They all convert to telecom or maybe O band. It's fine. Absolutely. Strain tuning, it's more of a dream if it works. So Matt thinks, so he's the experimentalist who's doing a lot of cool work in this area. And if there is some sort of a clever strain engineering of the whole sample that can directly tune them, but yes, it's a very hard problem. It's definitely a hard problem. So, and especially because you tune here, you damage and you change the ZPL somewhere else, and it's even the theory of these strain-induced tuning of the ZPLs is not very well understood. 8 minutes. Okay, all right. So let me. Yeah, sure. Go ahead. Yes.
So these are more or less a quantum repeater of the first generation, but we also start in theory to think about the second generation, use error correcting codes.
Yes.
How far are we away from this
question.
candidate?
Given Arun's time indication, let me just jump to answering your question, because that's an important part I wanted to get to. So I'm going to show you a couple of things. So this slide is about how you can encode a dual rail qubit into an atomic qubit deterministically, in principle, using what is known as the Duan-Kimball scheme. I'll skip explaining this. It's a cavity-QED interaction. Misha and Marco's group have realized that in the lab. And I will just point you to these two papers. Take a look at these two papers and this more recent one, all of which address achieving spin-spin entanglement that approaches capacity. And how do you do that? Well, you have to encode multiple qubits in one optical pulse that interacts with a register of quantum memories. Because that's the only way you can get multiple entangled bits per mode of transmission. So what we do is that we use the GKP qubit. And you want to mimic the Duan-Kimball-like interaction, which is a controlled phase gate between your memory qubit and the GKP qubit. And the GKP qubit, if you know how it works, if a Z gate or a phase gate is just a displacement in the phase space. So a displacement in the phase space can be realized with a coherent state and a beam splitter. What if instead of a coherent state, I put a coherent state and I bounce it off of a cavity that has a memory in the equal superposition of up and down, I create an alpha 0, alpha up plus minus alpha down. So I displace and undisplace the GKP at the same time in superposition. So that does the control Z-like interaction. Rest are details. And turns out that you can approach capacity in terms of spin-spin and heralded entanglement generation over a link with these GKP qubits. But I'm saying approaching, not achieving, because there is still an open question how to exactly achieve capacity. And I believe where Prajit's or our result falls short is that homodyne swap in the middle is where we are losing capacity, that there is some more clever recovery operation is probably needed to get to capacity. But I'm going to skip this part. And this is the scheme that and the plot that shows how close to the capacity we can get. So the constant factors, not much, but it's still not satisfying that we are not at capacity. So it'll be good to work that problem out. And by the way, this problem I was telling Matthew the other day, solving this problem also could help us with this problem that Christian asked in the morning about what about DV entanglement for entanglement assisted communication. It's very closely related, these two problems. So there might be some connections one could explore. Okay, so let me skip the discussion on the ZOM source. But the ZOM source is a proposal that we had proposed for a midpoint source-based entanglement scheme that uses two SPDC sources and a spectrally multiplex swap to generate photon-photon entanglement. That works much better than an SPDC source. But the main crux of the story was that these midpoint source-based schemes are much better for remote entanglement generation because of their resilience to excess noise compared to midpoint swap-based entanglement schemes. So let me skip these calculations. Okay, let me come to this question of error correction that Christian just asked. So now let's say it doesn't matter if you use dual rail, single rail, GKP qubit, your end product is two spins into remote sites that are entangled, some state rho AB. Now, before you use it for further processing or to build a quantum repeater, you need to distill, you need to purify that entanglement. So the way that works is via the entanglement distillation. So, well, the first is that you need multiplex arrays of qubits. There are different ways in which people are pursuing multiplexing qubits. The left side, these are photonic integrated chips that Dork England's group is pursuing. In Europe, Ron Hansen's group is doing very similar work with tin vacancies in diamond that are coupled to PICs. The right-hand side, that diagram is of a system that Matt Eichenfield and Chao Han-Soo in my group, they are collaborating on. It's a two-dimensional array of diamond nanopillars embedded with silicon vacancies in diamond. And the photons are collected by a MEMS scanning mirror with a fiber tip that collects the photons. Doesn't matter which way you do it, you have many qubits in one array. And then the way entanglement distillation works in principle is that you apply a n qubit unitary to both sides, and you measure off n minus k qubits. And you get k qubits on both sides that are entangled in good quality entangled states. Remember, this was my first slide in the quantum part. So you go from n poor quality to k good quality. What's the problem with this approach? Well, I told you the rules of the game for color center qubits. You are not allowed to do 2 qubit gates between 2 color centers. That's very hard. But you can herald an entanglement generation is fine, but it's probabilistic. You can do any single qubit gates on the electron spins. You can do any 2 qubit gates between the electron and the nuclear spin within the same atom. So what we said is that this kind of entanglement generation distillation scheme is very hard because it requires you to do inline quantum logic, 2 qubit gates and single qubit gates, one after the other. That's very hard. So what we did is that we came up with a different scheme. So this, I think this should appear in PRL today or tomorrow. It should come out. I have not checked if it's appeared, but this is a paper. It's on our archive. You can take a look. The idea is to use the measurement-based model of quantum computing. And let me explain you what I mean. So remember the midpoint swap way of generating entanglement that I talk about, where you have 2 atomic emitters emit photons that meet on a beam splitter to generate spin-spin entanglement. You can repeat that process along with shelving those entangled states into the nuclear spin qubits and regenerating entanglement many times to generate a complex state. So for example, that the graph state that I'm showing there is a state that you're generating on the nuclear, that is living on the nuclear spin qubits of a whole bunch of color centers in an array. And that's something, all the pieces of which have been done by multiple groups in the world. Nobody has generated that big a state, but you can, in principle, scale things up. And then the midpoint source that I did not talk about, the ZOM source, that will spray these entangled photon pairs that go to 2 sides and get loaded on the electron spin. So those are the long distance entangled states, the n noisy bell pairs. And the way the entanglement distillation scheme now works is that you have this n plus k qubit entangled state on both sides, which serves as your code, your substrate for entanglement distillation. And then what you do is that you apply 2 qubit Bell state measurements, notice on the electron and the nuclear spins of the same atoms on both sides. And this is far easier to do. It's the one single RF hyperfine control sequence that applies the Bell measurements on all of the qubits in that array. And then once you're done, the k qubits that are unmeasured on the 2 sides will be in that entangled state. It will be in the good quality entangled state. So there's a recipe to map any stabilizer code into a graph state, and we prove that in this PRL that will be published, that the properties of the code translates into the property of the entanglement distillation. Question, Bulat?
So this would be basically kind of an alternative, well, not alternative, but something similar to what PsiQuantum is doing, which is where Shlesha is involved, right?
Ashlesha is now in PsiQuantum, yes.
But from the public,
But PsiQuantum is doing a photonic cluster state for photonic quantum computing. Here you have a cluster state among the atomic qubits. And I'll talk to you about, so there is connections. You're absolutely right, Bulat. So it smells of FBQC, fusion-based quantum computation, because you are doing those 2 qubit measurements to do the computation. So we took inspiration from FBQC for this design. But let me show you the simplest version of distillation, which we all read in textbooks. That's the Deutsch protocol you're seeing. Okay, so this is your 2, so Alice and Bob have, this is a Bell state, and that's a Bell state, okay. And the way distillation works is that Alice and Bob both apply a control knot in a single qubit Pauli measurement. And if it succeeds, they're 1 qubit that are left over on both sides, they are in a higher fidelity than the original qubits, if your original fidelity was above a certain threshold. That's how distillation works. So first, our protocol, the measurement-based protocol, what will it translate to? It translates to what I'm showing over there on the top right. The red entangled states are your noisy entangled states. So there are 2 of them. And the 3 qubit state that I'm showing is a 3 qubit line cluster state. Then what you do is that you do 2 fusion operations. And those 2 fusion operations translate into 1 entangled state between the blue and the blue. That's your purified entangled state. Now, see another example. It's a 422 code. So you have 4 noisy entangled states. Those are the orange qubits. And now I have a 4 plus 2, 6 qubit graph state locally. And you have 4 fusion operations on both sides. And you'll go from 4 noisy states to 4 better fidelity states on those green qubits. And you can do the performance evaluation of all of these different codes. There's hypergraph product codes we looked at, and different, my postdoc Yushi, he did this calculation. And then there's a question of how do you realize that? How do you build that in the lab? I told you the rules of the game. For the allowed operations, you can generate any electron spin-spin entanglement probabilistically, but it's heralded. You know when it succeeded. Number two, you can do any electron nuclear spin 2-qubit gates within a single color center. That's deterministic. And the third is you can do any electron spin single qubit measurement. The only big thing that is missing there is any 2-qubit gate between 2 electron spins. So let's see how you generate that 3-qubit line cluster state. So those are the steps. So you start with the first defect and the 3 defects. Okay, 3 defects. You start with the first 2. You follow the first Prajis protocol I showed to generate entanglement between the 2 color centers. Use the dual rail scheme, for example, or GKP, doesn't matter. You get this entangled state between the 2 electron spins. You wait until you succeed. You keep trying. Once you get that, then you apply a swap gate, which is a 2-qubit gate, which we can do. Misha's group has done that in a paper a couple of years back at 97% fidelity. You move this entangled state, the red entangled state, to a blue entangled state, to the nuclear spins, right? Now the electron spin of that second defect has been freed up. That's the optically active one. So it can emit photons again and try and attempt an entanglement with the defect 3's electron spin. And you again keep trying until you fail. And then once you succeed, you have this red entangled state between defect 2 and defect 3. Now what you do is that defect 2 have both 2 qubits, one entangled with the right, one with the left. But one is electron spin, one is nuclear spin. So you can do a 2-qubit entangling gate. You can do a 2-qubit C0 gate. And then after that C0 gate, you kill that electron spin qubit by making a measurement. And the other side, the defect 3, you move the electron spin qubit to the nuclear spin qubit using a swap gate. And this set of 4 sequences gives you a 3-qubit line cluster state. Now there's an open question, which a student of mine, Aparna, she's working on. Said, I give you a graph state. Here's the code that comes from Yushi's work on some stabilizer code. What is the most resource efficient way to compile that into the laser sequences to do the photon emissions, to do the electron spin-spin entanglement, the microwave pulse sequences to the single qubit electron spin rotations, and the RF hyperfine pulses to do the 2-qubit electron nuclear spin gates to generate a given graph state. And I don't know the answer to that. So those are the open problems. And there's lots of interesting questions on finite length performance of distillation, which people here might be interested in on the theory side. Okay, then another question about if you are familiar with the measurement-based model of quantum computing, the original paper in 2001 that showed how you can take any quantum circuit and map it into a square grid cluster state. And you just make single qubit measurements in the cluster state, you can embed any quantum computing problem. But what it didn't guarantee is that the most resource efficient usage of that square grid. So if you give me a square grid, ask me to embed a quantum circuit into that, I don't have to follow the Rausendorf policy. Maybe I could have the qubits go in some snake-like pattern and use the least number of qubits in that square grid. So again, rather than going into the details, I'll have you, if you are interested, take a read of this paper. My former student, Ashlesha, she's now a scientist in PsiQuantum. So she decided, so this was a hard problem. So she decided to outsource this problem by making a computer game. If you have played the game of Tetris or any Tangram puzzle, I think you will like playing her game. We are going to put it on a beta version of that on our website soon. This game can be played by an 8th grader without any quantum computing knowledge. You're basically tiling puzzles. But unknowingly, if you score high on her game, you will be finding more and more resource efficient embeddings of a quantum circuit into the cluster state model of quantum computing. Okay, and then after that, there's a whole host of work once you have purified that link. Then there's the question of building repeaters, networking algorithms, and designing entanglement for sensing and other applications, which I obviously don't have time to go into. But I'm happy to talk to people if you are interested in this workshop. Well, to summarize, hopefully this was, I alluded to some interesting problems that touched everybody's interest here in this room. We talked about 4 distinct regimes of classical laser communications where quantum could play different types of roles. There are different stages of maturity and different kinds of improvements. Some is capacity, some is, in some cases, entanglement assistance. Some cases, it's high, low latency and so forth. And then I touched on quantum communications, focusing more on entanglement generation across a single link for supporting two-way quantum communications. All right. With that, I think I'm going to acknowledge my research group and my funding agencies, and happy to take any more questions. Thanks.